Hello everyone, my name is Adarsh. I'm a master's student studying computer science at the Saarland University in Germany. My research interests include graph representation learning and geometric deep learning.
We challenged researchers to explain their work across three levels of difficulty. First, they'll simplify their research for a young learner. Then, they'll level up to explain it for a student. Finally, they'll dive deep for a fellow researcher.
So we primarily work on graph neural networks. These are specialized AI or machine learning algorithms, loosely speaking, that work on graph structured data. I mean, you must already be familiar with some of the graphs that you encounter in your daily life. For example, social network, right? If you're using Facebook or Twitter, that's like a giant network where all the users are nodes. And if you follow them or if you send a friend request or something, then those you form like an invisible link between those entities or nodes, and that is called as the edge, right? So a graph has two constituent parts, the nodes and the edges. So we are trying to address two challenges, oversquashing and oversmoothing. So to understand oversquashing, I have a simple example. So imagine you're in a class with around 40 to 50 students, right? And you have your friends, and you all of you have been dispersed across the classroom, right? Because your teacher thinks that if you sit next to your friends, then you won't learn because you might be busy talking to them or something. So you have been dispersed across the classroom. Some of your friends are sitting way in the front, some are sitting in the back. You're somewhere in the middle. You and your friends have come up with a clever strategy of talking in the classroom by sending messages, right? You write messages on a piece of paper and then you pass it to your neighbor till it reaches the intended recipient, right? So this is exactly how graph neural networks also operate. They operate by sending messages, right, to their neighbors and then updating the representation. For example, if the task is to decide on what time do you guys want to meet for a movie, and you send out a message saying that, oh, what time do you guys want to meet? And you pass it to your neighbor till it reaches the intended recipient. But it's possible that due to the distance involved, right, because your friend might be sitting way far ahead, right? So this message might not reach to them because, for example, it could be for many reasons. For example, the person sitting next to you might be reluctant to pass these messages, or the person sitting next to him might be absent. So there is like a huge gap in the classroom so that your message might not reach. Or maybe the professor is making rounds in the classroom, so it's difficult for you to sneak around and pass these messages. This is exactly the problem of oversquashing, where the messages might not get through because of these obstructions. Another issue is oversmoothing. So again, to illustrate this, imagine you're taking a art class in your school and your professor has given you a task of painting something complex but with just three colors. So he's given you, say, red, blue and yellow, and for your friend he's again given some three different colors. What you guys soon realize is that you can mix some of these colors to obtain a new exciting color. For example, if you want green, you can mix blue and yellow and then you get green. You do this, but again you'll realize that if you do this multiple times, like if you keep mixing these colors multiple times, all of you will end up with the same brown muddy color, which is useless for everyone involved. So this is the problem of oversmoothing, where if you mix these messages too much, all of the messages, it becomes similar and it's useless for the task. So this is exactly the problem with oversmoothing as well. And in our work, we try to propose methods that allow us to modify the graph structure in some way so that these messages reach in a better way, or you try to make these obstructions go away by modifying the root of these messages so that those messages reach the intended recipient and the information can be updated nicely. So we said that we are using graph neural networks which operate on graph structured data. And the task that we are trying to solve is called as node classification. What this basically means is, if for example, in a social network, if you, based on the user's likes and preferences, we want to predict, say, for example, their demographic. Or for example, in an e-commerce network, we want to predict if certain users will buy, are they frequent buyers or not. So basically you want to classify your nodes based on some criterion. And we saw that if we want to apply graph neural networks, we will face some issues called as oversquashing and oversmoothing. To illustrate this, imagine you have a graph which looks like a barbell, right? So this is basically called as a barbell graph. So you have two communities which are bridged by a single edge. all the information that comes from this community, if it has to reach this community, then it has to go through this single edge only. So this single edge constitutes a bottleneck edge. It's like all the messages that are coming from here have to be squashed and sent through this single edge to reach this community. That is why this term of over squashing exists. Based on some criterion, what we can do is we can modify this graph by adding edges between these two communities. So instead of just single edge, you have like multiple edges now bearing the load. So there is no one bottleneck edge. But turns out if you do this, you might end up adding edges between nodes of different labels. What this means is when you're trying to aggregate information, like pass messages and aggregate information, you have connected nodes which have different likes, which means, for example, in a social network, you're basically added a link between two users which have completely different tastes or different likes. And we don't want this to happen because then our GNN will think, our graph neural network will think that both of these should be mapped to the same representation because there is an edge existing between them. And graph neural networks operate by sending messages. Essentially, what we have done is we have tried to address the problem of over squashing by modifying the graph. But by doing so, we have inevitably introduced the problem of over smoothing. So in this work, like our work, we try to show that both of these are not a trade-off. You can address over squashing by not making over smoothing worse. And we do this by proposing a graph modification strategy based on a criterion called as the spectral gap of the graph. That would be getting a little more technical of what we are trying to do. Current literature posits that this over squashing and over smoothing are kind of like a trade off that needs to be balanced. So, one of the strategies to mitigate over squashing is to modify the input graph based on some criterion. And these criterion can be something like the discrete Ricci curvature of the graph. So, you can essentially treat your graphs as discrete manifolds and you can define a curvature based property on these graphs. Some of the works show that there are edges, like negatively curved edges, which cause these bottleneck. And if you delete them and you add positively curved edges, then you can try to address this problem of over squashing. So if you have a barbell graph with two communities bridged by a single edge, and if you were to look at the spectral gap. So what is the spectral gap? Basically, the connectivity information of the graph can be written in a matrix form called as the adjacency matrix. And if you were to normalize this to obtain the normalized Laplacian of this adjacency matrix, and if you were to perform the eigenvalue decomposition of this matrix, and if you were to arrange these eigenvalues in ascending order, and if you pick the first non-zero eigenvalue, this is called as the spectral gap of the graph. So what the spectral gap indicates is how well information can diffuse on a graph, right? So a smaller spectral gap value implies there is a bottleneck edge, which means over squashing will happen. So what we want to do is we want to optimize this quantity. So why don't we modify the graph which maximizes this spectral gap, because this is directly tied to how information flows on the graph. We can add edges based on this spectral gap which maximizes the spectral gap. But if we do this, you might end up adding edges between nodes which have different labels. What this means is you will make over smoothing worse. What we propose is we leverage this counterintuitive phenomenon called as Bayes paradox. What this basically says is if you were to add an extra road because to prevent traffic congestion, for example, as I said, like if you have two cities bridged by a single edge, and if you were to build an extra road hoping that it will prevent or if it will alleviate the traffic congestion, it actually makes the traffic worse for all the commuters. So this is like a counterintuitive phenomenon. You would expect that adding an extra road will actually bring down the commute time, but because of this Bayes paradox, the commute time actually increases for all the travelers. So we leverage this insight to essentially show that you can delete edges in a graph, which will actually increase the spectral gap. This is a little counterintuitive because usually to increase the spectral gap, you need to add edges. And if you delete edges, the spectral gap decreases. But because of this phenomenon of Bayes paradox, we show that you can delete specific edges, which will increase the spectral gap. And by doing so, what we have essentially done is we have increased the spectral gap, which means the problem of over squashing has been alleviated. And we also show through like a comprehensive set of experiments that by doing this, we don't make over smoothing worse, because it's highly likely using our method, especially in graphs which are called as heterophilic graphs. That is, your neighbors might have different labels, right? So graphs can be homophilic graphs and heterophilic graphs. Homophilic graphs means like nodes are connected to like nodes. Like it's highly likely that your neighboring nodes also have the same labels. But in heterophilic graphs, that might not be the case. Your neighbors might have different labels, right? So we show that our method is highly effective in heterophilic graphs because it's more likely that our method deletes edges between nodes of different labels, which would allow us to not make oversmoothing worse. We have proposed a graph rewiring strategy by leveraging this insight from Brace paradox, which says that you can delete edges, increase the spectral gap, mitigate oversquashing, and also ensure simultaneously that you don't make oversmoothing worse. Finally, also as an additional bonus application, we show that our method can help identify graph lottery tickets. So what this means is, so there is this hypothesis called as the lottery ticket hypothesis, which essentially says that if you start with a dense over-parameterized network, and if you repeatedly, like iteratively prune and train like the unimportant parts of the network, then you will obtain a smaller sub network which is contained inside this dense over parameterized network, which can actually match the performance of the original dense network. So these are called as the winning lottery tickets. And since our method also prunes edges, so we use this method to also identify sparse graphs and sparse network, like sparse graph neural network, which can obtain like competitive performance if we were operating on the original graph and if we were using the original dense or parameterized GNN.